So in chapter 1, we're going to briefly look at structure and bonding and also acids and bases. So it's going to be a little bit of a review of general chemistry, and then we go into some acid and base chemicals. What is organic chemistry? Organic chemistry is living things. They're all made up of organic chemicals. Proteins, which makes up hair and nails. DNA is organic chemistry. This controls your genetic makeup. Foods are considered organic chemistry, and medicines are also organic chemistry. Now you can see lots of different medications shown to the right here. We have Vioxx, Lipitor, those are cholesterol medicines. OxyContin, you may be familiar with that, very addictive drug. Cholesterol, and benzylpenicillin. Previously, organic chemistry was defined in the mid-1700s as a compound that came from living organisms, such as plants and animals. The current definition of organic chemistry, however, is just the study of carbon-containing compounds. 90% of more than 30 million chemical compounds have carbon in them. And for the most part, the organic chemicals contain the elements that you can see colored in the periodic table. They have hydrogens, the carbon here is the most important one, nitrogen, oxygen, a few of the halogens, and also phosphorus and sulfur. So those compounds combined with carbon are organic compounds. If you recall from general chemistry the structure of an atom, we have a positively charged nucleus, which is in the center. It's very dense and contains protons and neutrons, and is also small at 10 to the negative 15th meters. The negatively charged electrons are in the cloud, which surround the nucleus. So you can see the nucleus here. Protons have a positive charge, neutrons have zero charge, and the electrons have the negative charge. So you can see the negative cloud surrounding the neutron. S and p orbitals are the most important in organic and biological chemistry. S orbitals are spherical and have the nucleus at the center. So this one here is an s orbital. P orbitals are dumbbell shaped or kind of look like peanuts, and the nucleus is at the middle. So you can see that nucleus there, and then for the p orbital here. And d orbitals are elongated dumbbell shaped, and the nucleus is at the center there as well. This one is the d orbital, and there's the nucleus in the center in green. Each of the shells are 3 perpendicular p orbitals of equal energy, and the lobes of the p orbital are separated by a region of no electron density, which is referred to as a node. There's no electron density in here, and that is considered the node. When we look at different orbital diagrams, an s shell is lowest in energy. This can hold 2 electrons. So any of these orbitals can at most hold 2 electrons. The first shell, which is the 1s, holds only 2 electrons. When we go to the second shell, this has a 2s orbital and also has 3 2p orbitals, which can hold each 2 electrons as well, for a total of 8 electrons. And the third shell, which is an s orbital, 1s orbital, and then 3 p orbitals, and we have 5 d orbitals that can hold 10 electrons, for a total of 18 for the third shell. And these increase in energy as we fill more shells. Kekulé and Cooper independently observed that carbon always has 4 bonds. The atoms don't have specific directions, but they want to be as far as possible from each other. So if we look at a carbon, this is the structure of methane. This is a carbon with 4 hydrogens on it. This is what they've observed. And what they notice is that these hydrogens want to be as far apart as possible, and this is what it looks like in 3D shape. So this is referred to as a tetrahedral shape, and they get that from this geometric structure here, where these are as far apart as possible. You might notice that there's lines that are straight. We have some dashed lines and some wedged lines. The 2 lines that are just straight are representing bonds in the page plane. So if you're looking at the lines of your paper, these are in the plane with your paper. The dashed lines are for bonds that are going away from your paper or sticking out the back of your paper. And then the wedged line refers to a bond that's coming out of the paper. So this would be your tetrahedral carbon atom. Each carbon atom, 4 bonds. When we draw the 3D shape, there will be 2 bonds in the plane, 1 bond sticking out and 1 sticking back. So if we were to draw CH2Cl2, which is dichloromethane, using solid and wedged dashed lines to show its tetrahedral geometry, I would start first with just drawing it flat. So carbon, we know, makes 4 bonds, and there's 4 atoms here. So I have H, H, Cl, Cl. So this would be CH2, Cl2. This is all flat in your paper. If we want to showing wedges and dashes, we can choose any 2 things to be flat and then the other 2 wedged or dashed. So if I opt for my hydrogens to be flat, one of the chlorines must be wedged, the other one must be dashed. You could also draw your chlorines flat, a hydrogen wedged, 1 dashed. One of each of these can be in the plane, and you can draw that. So there's different ways to draw them, and which makes sense because you can pick up a molecule and rotate it around any way you like. So next you can convert the following structure into a structure using wedged, normal, and dashed lines to represent the 3D structure. So this is what we're seeing here. We have to decide what is in the plane, what's coming out, and what is going away. So to me, this looks like this is what is in the plane because it looks flat. So if I were to draw this, the black balls represent carbon, the gray ones are hydrogen. So this is carbon. And on this particular carbon, that one looks like it's going back, so I would draw the dashes. This one looks like it's coming forward, so there's a wedge there. This one is pointing back, and that one is coming out at you. So this carbon has 2 bonds in the plane. One is wedged, one is dashed. This carbon has 2 bonds in the plane. One is wedged, one is dashed. Atoms can form bonds because the compound that results is usually more stable than having the atoms be separate altogether. Ionic bonds are those that are in salts. They result from electron transfers. Covalent bonds are bonds that form in organic compounds, and that's resulting from the sharing of electrons. Ionic bonds are resulting of the sodium ion giving all of its electrons to chlorine, and chlorine holds on to them. In an organic compound, the electrons are shared equally between the 2 atoms. We can represent organic compounds in different ways. There's the electron dot structures, which you've seen previously, are also known as Lewis dot structures. So Lewis structures are electron dot structures, which show the valence electrons of an atom as dots. The valence electrons are shown as dots, as we've seen before. And notice also that oxygen and nitrogen, which have extra lone pairs, those electrons are shown as well. And the calculate structures have the line drawn between the 2 atoms. which indicates that there is a covalent bond there represented by the sharing of 2 electrons. In a stable molecule, the atom will have 8 electrons, which is a completed shell, or for hydrogen, there's only 2 electrons there. Each of these atoms that are not hydrogen will have a complete octet. These show all of the individual electrons. You can see carbon has the 4 electrons, hydrogen contributes 1, and those are each forming a bond. There's also the Kekulé structures, which just shows the bond as a line instead of 2 individual electrons. So this is what you can see for a carbon. This is nitrogen, oxygen, and a carbon that's bonded to an oxygen. Carbon here, you notice, is making 4 bonds. Nitrogen makes only 3 bonds. Oxygen makes 2 bonds. Here carbon has 4. Carbon can form 4 bonds still, 1 to oxygen. This oxygen has 2 bonds. When we look at these atoms, these are the main ones that you'll need to know for organic chemistry. We don't need to be concerned about electron dot structures for the rest of the periodic table. Hydrogen has 1 bond. Carbon makes 4 bonds. Nitrogen has 3 bonds. Oxygen 2 bonds. And the halogens have 1 bond available. If you have a hard time remembering how many bonds each atom makes, you can look at the electron configuration. So for carbon, it has 1s2, 2s2, 2p2. This first shell is already full. There's no electrons available for bonding here, but with 2s2 and 2p2, these have 4 valence electrons still available for bonding. 4 valence, and each of those is available for a bonding, like I said, and that's how we can remember how many there are. You could also look at the group number of, the group number here is 4, 5, 6, and that is 7, which tells you how many electrons there are. And as you put them around the atom, this would be 1, 2, 3, 4, 5. 2 of these are lone pairs, and that's why we have 3 bonds here. This is 1, 2, 3, 4, 5, 6, and these have 7. These are all paired up, so there's 1 bond available. Those are the 2 tricks you can use to remember how many bonds each of those atoms make. For drawing structures of organic compounds, ethane is one that has 2 carbons. This is C, C. And there's enough hydrogens around here to fill in the rest of the remaining bonds. So this ends up being C2H6. Propane has 3 carbons. And each of these carbons has 4 bonds. Each of the hydrogen has 1 bond. Butane has 4 carbons. And pentane has 5. Here are a couple of practice problems. You can pause the video if you want and try to work out the problems on your own before you come back to look at the answers. We're looking at drawing both electron dot and line bond structures for chloroform. Chloroform is CH3Cl3. You can start with carbon, which has 4 valence electrons. Hydrogen has 1. And chlorine has 7. And we have 3 of those. One of these can form a bond together. One of these can, and then the other chlorines can as well. So my resulting electron dot structure would look like this, and the line bond would look like this. In the line bond drawing, you don't need to include all of the electron lone pairs for chlorine. If we look at the next problem, it's asking what is the likely formula for the following. And we can figure this out based on the number of bonds that carbon needs to make. Carbon has 4 valence electrons, so it needs to make 4 bonds. This is only bonding to chlorine, so this one needs to be 4. Nitrogen is in group 5. It has 5 electrons. 2 of these are already paired up, so it's available to make 3 bonds. Hydrogen is the only thing it's bonded to, so this should be 3. For CH blank OH, it is, again, carbon makes 4 bonds. Oxygen has 6. 1, 2, 3, 4, 5, 6. So there's 2 bonds available. Hydrogen does 1. So if I look at this carbon, it has a bond to H. Oh, this is to an H, so this one's happy. So we need to fit in 2 more H's here in order to fill that. So this carbon has 4 bonds, this oxygen has 2. So why can't an organic molecule have the formula C3H9? If we try to draw this out, I have 3 C's, this has 4 bonds, this has 4 bonds. I have 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. All of my carbons have 4 bonds, so I can't fit any more on there. There's not enough bonds available. If we look at valence bond theory, covalent bonds form when 2 atoms come close to each other so that a singly occupied orbital, another one, overlaps. We have 2 individual s orbitals in these hydrogens. They come close together where their orbitals can overlap and they can form an H2 molecule. Valence bond theory was developed in order to model and describe the covalent bonding. In the valence bond theory, electrons are paired in overlapping orbitals and are attracted to nuclei of both atoms. So I'm going to use the E minus here to represent electrons. So the electrons are attracted to nuclei of both atoms. A hydrogen bond can result from the overlap of 2 singly occupied hydrogen s orbitals, like we said here, these 2 singly occupied ones. So when 2 of these s orbitals get together to form a new one, it forms a sigma bond. So if we had H got together, it forms H. This is a sigma bond. So 2 s orbitals form a sigma bond. And that is a face-on or head-on bond. Bond strength is the energy that's released when a bond forms. And the bond length is the optimum distance between a nuclei, leading to maximum stability. So there's going to be an optimum bond length versus bond strength. This is too close together, this is an appropriate bond length, and this is too far apart. If we look at the sp3 orbital and structure of methane, which is CH4, a carbon has 4 valence electrons. Like I mentioned, that 2sp2 and 2p2. In CH4, all of these are identical, or tetrahedral. So an sp3 hybrid orbital has 1 s orbital and 3 p orbitals. And those will combine to form 4 equivalent unsymmetrical tetrahedral orbitals. So there's 1 s and 3 p's, which make the sp3. This was figured out by Pauling in 1931. So the sp3 orbitals have a carbon overlap with 1 s orbital and 4 h orbitals that are identical. So each CH bond has a strength of 439 kilojoules per mole and a length of 109 picometers. This is the model of CH4. This is the space filling. This is the Kekulé structure. And then we have the ball and stick one here. So this carbon has bonds that are equal for each of these CH bonds. We can see the 2 lines in the plane, and then the wedge and the dash here. The bond length of each of these is 109 picometers. And the bond angle between these two here is 109.5. So the bond angle for each HCH is 109.5. This is the tetrahedral angle. If we have two carbons that are bonded together by overlap of an sp3 orbital from each carbon, that is what we see in ethane. So a CH bond in ethane is 421 kilojoules per mole, while the carbon-carbon bond is 154 picometers long and is slightly less strong at 377. All of the bond angles of ethane are tetrahedral. So this bond here is 109.5. So we have the two carbon sp3 atoms will come together to combine to form the sp3 sigma bond. And then we have the ethane here in the Kekulé structure and then the ball and stick figure. So you can see the different bond lengths here. Other kinds of hybridization that we will encounter include sp2 and sp. An sp2 orbital comes from an sp2 carbon, as we can see here. These are made up of sp2 hybrid orbitals, have one 2s orbital that combines with two 2p orbitals, which gives it 3 orbitals. And those are spp or sp2, which results in a double bond. So you can see this double bond here. We have an sp2 carbon. The green ones are sp2 orbitals. The green orbitals that you see are sp2 orbitals. And then we have one p orbital. When the p orbitals combine, these get together, this forms a pi bond. And this is also the other part of the pi bond. This is where the electrons are. This is the bonding part. This is the non-bonding part. And where the carbons formed that first bond together, that is a sigma bond. So sp2 orbitals are planar, which means they're flat. And they have bond angles of 120 degrees there. So the sp2 orbitals are planar and flat. The remaining p orbital is perpendicular to the plane. So we get two sp2 hybridized orbitals with a head-on overlap, form a sigma bond, and then we have p orbitals that have overlap side to side, giving us a pi bond. So if you think of two pregnant ladies with their bellies sticking out, if they were trying to give each other a hug head-on, you'd have the two pregnant bellies touching each other. That would be your head-on sigma bond. And if they were then going to try to shake hands while their bellies were touching, that would be your side-to-side pi bond. So again, sp2 bond is double bond. The sp bond is a triple bond. It has a carbon with a 2s orbital that hybridizes with a single p orbital, which gives two sp hybrids. So two of these p orbitals are unchanged. These are linear and 180 degrees apart on an x-axis. So two p orbitals are perpendicular on the y and the z x-axis. So this would be one sp orbital, one sp hybrid, this is the other. And they will combine here to make the triple bond, which we'll see in the next slide. So we have two sp orbitals that form this sp head-on, and that forms this sigma bond here. The two p orbitals here are going to form that pi bond. So the sp orbitals are responsible for the sigma bond, the p orbitals are responsible for the pi bond. So two sp hybrid orbitals from each carbon form the sp-sp sigma bond. So sigma bond comes from sp-sp orbitals, and the pi bond comes from the p orbitals. Just like before, the sp are going to have that head-on overlap, and then the p orbitals will have the sideways overlap. And you can see the space filling picture here. You can see that that is 180 degrees. This is linear, and that's what the structure of C2H2. So if we compare the carbon-carbon and carbon-hydrogen bonds in methane, ethane, ethylene, and acetylene, you can see the different structures here. The bond strength increases as you increase the number of bonds, and the bond length decreases. And you really want to pay attention to the carbon-carbon. The trends are the same for hydrogen. But if we're comparing carbon-carbon bonds here, the 377, 728, 965, these bonds are getting stronger. If we look at kilojoules per mole, and the bond length goes from 154, 134 to 120, are getting shorter. The bond strength increases with the number of bonds, and the bond length decreases with the number of bonds. And that's because the electrons are being held closer together. And the CH bonds have the same trend where they increase, and the same with the bond length. Okay, so we are tasked with drawing the electron dot and line bond structure for acetaldehyde, or CH3CHO. So we want to draw this Lewis structure, or the Kekulé structure first. So I have C, H, and sometimes when organic compounds are written out, the order in which it's written kind of is an indicator as to how things are put together. So I have a C with 3 H's bonded to a C with an H and an O. So I'm going to look at this and notice that this carbon has 4 bonds. This one only has 3. Oxygen is only having 1. Oxygen has 6 valence. 1 of them is used here. Carbon has 1 left over. So what I'll do is join these 2 electrons together and make a double bond there. Okay, so that is the electron dot structure for acetaldehyde. So what types of bonds are present? So all of these bonds here, the CHs and the C to C, those are sigma bonds. And that is the CH, the C to C. Those are the sigma bonds. And I see I have a double bond here, which means that this carbon is sp2, and this is forming a pi bond. That's a C to O is a pi bond. What is the hybridization of each carbon? This one here with all the single bonds, that is an sp3. This one here is sp2. The bond angles for sp3 are 109.5. For sp2 are 120. So next we want to draw an electron dot structure for acetonitrile, which is CH3CN, and then it tells us that we can have a carbon-nitrogen triple bond. So again, if we look at how this is written out, I have a C with 3 H's to a C to an N. Carbon has 4 electrons, nitrogen has 5. And we're told that the CN has a triple bond, so this is going to become, those electrons come here, these come here. And then I have electron lone pair left over. And that's how we would draw the triple bond and this structure.